Hi, my name is Pedro Fonseca. I work on the water treatment business, but I'm here to present you prototyping interface tools for data exploration in virtual reality environments. My presentation is already downloadable, and although there's an abstract to this presentation, I hope that my introduction kind of sets the mood. This is, not so scientific turn presentation. The main motivation for doing it is to try to find an excuse to get a virtual reality headset through our serious work that we do every day on Mathematica. A little bit as we did for the Raspberry Pi, yes? Like it gave us an excuse to start using one. So, some basics about the topic. Well, we know that we have information coming from a lot of sources that can be visualized in 3D. This information can be actually 4D, that is, it belongs to one point in space and it has one specific value. It can even have a value that is actually a vector, and so it can be of 5D. And it can have many other dimensions. It can be transient in time. It can be from a real world, or it can be from a computation, like computational fluid dynamics and other type of calculation system. To see this information, we typically rely on plots, headsets are becoming more and more interesting for everyone, yes, not just for the games. And so there are a lot of interesting alternatives to see this kind of information from within the information itself. Now we have here some examples of very cheap systems to a little bit more expensive to extremely expensive, yes. And of course, I'm sure that everyone remembers probably the most expensive of them all, yes. Let's hope we get there someday. And we know that this is becoming extremely popular to talk about this topic. And so I thought, well, why not introduce it into the world of Mathematica? Because in the last year's conference, I don't think there was a talk on the subject. This year, we already see a lot of stuff on it. We have Oculus Rift downstairs, so that we see that the interest is starting to get there. But, is it enough for me to justify buying a virtual reality headset? Let's see. Well, in Wolfram Language, there are actually functions that are very well tailored for presenting volumetric information on the screen. Why am I talking about volumetric information? Well, because typically we see on the media talking about 2D shapes in a 3D world. And that is kind of the most common. And so I thought, well, I have to talk about something different, yes? Something a little bit more rare. So these are the typical functions that we can use on Mathematica to visualize volumetric information. And we also have a bunch of functions that allows us to visualize this kind of information, but after having been transformed into kind of 2D information, yes. Again, and although repeating myself, this is just for the fun, and so let's see if we can get somewhere where we could say, yeah, I would like to have a headset. Okay. So this is what we typically see on virtual reality environments, so polygons. Here we already see a limitation of Mathematica, so we are inside the space shuttle example data, and I can't even see the controls inside or the satellite inside. And so there's missing information to really take it seriously, yes, because it's empty. It's an empty example, okay. But there is much more serious examples in the example data. Okay, it's a little bit slow to turn these kind of images around. Yes, this one runs pretty fast, But well, there is much faster. We can do much faster with volumetric rendering on the CUDA. And we all know that, well, this kind of information is getting more and more common. For instance, there's a project of some people trying to scan in 3D all the fishes species in the world. Yes, I think it's of extreme interest for all of us in this room. Of course, it might be of extreme interest for many people. The stereoscopic view, well, that is probably the most easy thing to deal with. That is to create the two images for the two eyes. There is a bunch of functions available. The community has put it out some demonstration projects about it, and I think they give a pretty good idea of what can be done. I'm actually using, I think, the code of this one for a small example of what can be done. Let me see. There are things that are quite heavy. Okay, so the first obstacle that we have is that we have to see through, and so in Wolfram Language this is quite easy. We have opacity functions that allows us to, let's say, vanish some of the data. That's great. Now, if we put this together with the things that we were seeing on the previous slide, well, we can imagine navigating ourselves on real stereoscopic view. Now, this is that's correct. So this is a crossed eye. This is a crossed eye projection, and so you would have to put your finger in front of your nose and trying to see it in 3D. It is actually not extremely difficult to do, but you can see that it is slow. So it is when we navigate. Well, it's kind of it's not really ready for virtual reality, I would say. It can be made much faster. Unfortunately, CUDA volumetric render has some problems in V11. They are already listed on Wolfram's bug list, and so that should be fine. Well, we need a way to control the way what we see as information. So coming back to our fish, I find the image extremely interesting. Wolfram Language mathematical interface has this kind of system that is called color function editor. It's actually, I don't think it's a good name because it's actually an opacity editor and a color function picker, because we can actually pick the color, but we cannot really manipulate the color or edit the color. So what we can manipulate is the transparency itself. So let's try to do an example here. Now, a color editor would look more like what is here, done by Kevin Daly posted on the community. And actually, this topic about opacity, calibration, opacity, color editing, etc. It's extremely important because we'll be inside this information, and so it has to be extremely fine-tuned for us to see anything. And so I think that what it is missing is some kind of opacity and color editor on the same interface. Now, I have copied here an image from another software that I think presents a good example of what we should probably have. This capacity of specifying an opacity and a color function for this kind of information is available on Mathematica. Unfortunately, they are both linked to the same data field. That is, we cannot have an opacity function acting on one field and a color function acting on another field. It's actually the fourth dimension that they are looking at, and so it restricts a lot on the things that we can do. There are many more details that I found here, like the fact that Image 3D uses just one color function for everything, and the density plot 3D actually divides it into opacity function and color function. Well, there are different things that we can see. There's also another limitation that we will encounter when trying to simulate a virtual reality environment inside of our head, is that once we join two images that are, let's just say two graphics that have different color functions, when we show them together, actually one picks the color function of the other. So we cannot join together two images of different color functions. And that is kind of bothering, because it difficulties us to do things like this. For instance, let's try to navigate to the inside of this engine. So again, it's a little bit slow, but we can get there. Imagine that you have your Oculus Rift or Vive or whatever, and that you are trying to get to that sphere. So we have to go slow because this is kind of, oops, we went a little bit too fast. And now let's imagine that to explore this environment, I would like to make a hole, like an X-ray around these spheres, yes? So I can actually make the hole, yes? Not exactly as I would like, because it's not possible to specify opacity for a given position. I can specify opacity for a field, for the fourth dimension field, but I cannot specify for a given voxel. And that is the kind of bothering for constructing interfaces to manipulate or to explore this kind of information. So, for instance, I can also specify an X-ray vision, a kind of X-ray vision, of course. It's a different way of seeing it. It's actually a high-range specification. But I cannot put both together, and that limits a lot of how we could explore this kind of information, like creating a hole in the wall and things like that. Okay, so there's a brief summary of the limitations that I find on this seeing through that mathematics allows us. One of the things is that I cannot specify opacity and color by position. It's only linked at the field itself, and I cannot join two different images with specifications different together. Okay. Now, when we think on tools, we can think of things like a flashlight, a spotlight that creates invisibility fields, some kind of burn utility that denses information on a specific area. Now, let's try to do this. So let's try to go inside the motor again and try to deploy one of these let's say invisibility flashlights. Yes, let's suppose that I see a hole there. Yes, and let's try to move this flashlight around. Okay, so this might be interesting to have as a tool. Yes, so we are prototyping tools to have with us when we have the casket on. So the helmet on, sorry. What could we think as tools for this? Well, this one, like a flashlight, could be interesting. That would just do matter disappear, yes? Let's put ourselves in the center to try to understand what it could be. It could be like a laser beam, yes, with an aura that just makes things disappear. Okay. So that could be a nice thing to have. Now, this is conceptually wrong because, well, when we think of a flashlight, we think of a cone, yes, because that's how the light is generated on a simple flashlight, and that means that we would be peeking through a hole, yes. So, like the cone should be inverted. It's because if we try to do matter disappear, but we just see through the cone, it's a little bit strange, yes? It's like peeking through a small hole. Yeah, so probably, well, we have to change this tool to something like that, an inverted cone with an area around us that has disappeared so that we can see a little bit further away than just a few centimeters from our eyes. And so this is probably what we are looking for. Now, that guy there has copyrights, okay? That's actually me scanned on 2015 conference. And we could also think on having a fading field from the person up to the limits of this invisibility field, yes? And so that would be like not make it totally disappear, but make it a little bit brighter, that area, so that we can see a little bit further away than just where we are, yes. There are some currently odd things going on when we try to do this with Mathematica that obviously was not thought from the beginning to be applied on virtual reality environments. Now, we have to think that when we use these flashlights and all these parameterization of opacity functions and things like that, we have the helmet on. And so how do we actually do it? Yes, do we take the helmet off and go to Mathematica and put the helmet on again? Well, of course, we would like to have this, that is, manipulate with appearance minority report. I don't know if Wolfram Research has that on their priorities, probably not right now. But I think that's more or less what we would like to have. Now, it's interesting to see that we can prototype these kind of things in Mathematica better than I would have guessed. For instance, there's me again with the helmet on, and I can project next to me a manipulation interface, and I can actually, I'm going to try to, it's very small, but probably it's actually possible to pick it up and to manipulate the function. It's difficult, but it's actually, there it is, yes. So the tools are there to implement insetted manipulation interfaces on our helmet, and that might be interesting for the future. But what do we exactly want to have next to us? Well, a lot of things. Here we see, for instance, the color manipulation function that I presented before. We may want to deploy slices of contour plots and things like that. And so we might want to manage them, make them disappear, create new ones and things like that. And so, yes, we need kind of an interface to walk with us, to explore this kind of information. And then there's the space mouse, because everything that is in the reach of our hands, that's great. But do we really have to walk the field up to a certain area of information in order to highlight it, make it disappear, create a slice there? Well, obviously we need kind of a pointer, yes? There are a lot of these things being imagined at this right moment by a lot of people. These are the things that come with, well, that can be bought as extras for the Oculus Rift and for the Vive. And so we already saw that concept on the previous image where we just had the blue line pointing as a laser, yes? And well, I think this is a kind of childish image, but I think it gives more or less an idea. That is, we are inside the field and we point it and we make things disappear. But, well, in a typical virtual reality environment, well, there's also audio that we could use nowadays, yes, because Mathematica now has audio, and so we could control these systems a little bit with audio. But in a typical virtual reality environment, well, when we point a laser, it hits a surface, because typical virtual reality environments are made of 2D shapes in 3D worlds. And so it's kind of clear where the laser hits. On volumetric information, we are just pointing a laser to a cloud. And so what does it exactly mean? How can I pick a cloud? How can I define where my laser ends? Yes, and so we could think of different ways of doing, like intensity degradation laser, a manipulation of a sphere through a distance, things like that. Well, let's try to see what we could do of these kind of things. So let's imagine that we are inside this information. This is actually a function. It's clearly not a scan from real life. And that we try to put a lot of things together on this image. And so we are fixed in a position, a given position, and we have our special laser, yes, and our special laser has these spheres attached to it that are positioned on high and low points of a given field, yes. And when I try to move that laser, now, I'm going to move with manipulate, but that would be me moving those kind of plastic accessories that come with the virtual reality headsets. You see that, yeah, it's a little bit sluggish, but we'll get there. You see that the spheres move to the new high and low points, and one thing that we could have next to us, it's the actually graphic of the field being traversed. And so in this way, I can actually pinpoint specific locations in space, even if my laser just goes through infinite, yes? And for instance, this thing is kind of hitting what is after it. And so let's try to make it disappear. Well, one thing that I can easily see is that, well, it is a high point, yes? And so I can probably pick that point, and okay, my green sphere became red. That's kind of easy. And now I could, for instance, deploy a segmentation of this space, yes? And so I'm pointing to a thing that is not near me, and I'm actually able to pick a specific point in space of this volumetric data without displacing myself to that point. Of course, I can pick another one. Let's try to pick another one. For instance, yeah. Now we have to raise a little bit. Yeah, good enough. Yes, we are pointing to it. Yeah, we are pointing to it. So let's try to choose that one. So that one was much further away, and I still can choose it. And well, I can actually, for instance, well, I'm going to hide the segmentation. So I have chosen a specific spot. And let's try to hide that amount of information so that I can see through as a way of exploring this information. It's a little bit slow because, unfortunately, we cannot manipulate opacity of locations. So I'm actually manipulating the entire data field. That is, I'm making all those fields become zero, so that they just vanish within our opacity function. But I think it can give an idea of the type of interfaces that we could develop, and there it goes. So we just made that piece of information disappear with a new tool that we developed, that is a laser that has high and low points. Okay, so it might be an interesting tool to have. And one thing that might also be interesting is to try to have data focus interfaces. That is, we have a lot of data to treat. Here we have 4D data, but we might have information of 5, 6D, and we are traveling through this information. And sometimes we have to pick based on fields that are not very, how to say, easy to individualize. And one way is to try to reduce the dimension of the data to something that can be like plottable in 2D. And in 2D, you can more easily choose with some kind of window or polygon or something like that. Let's try to use an example from the documentation. For instance, the documentation has this example here, and as a dimension reduction, we can reduce this information, this 3D information, into 2D. And actually, we can manipulate a data focusing window that will actually select specific points that are within the criteria of this dimension reduction. And we could imagine having this window next to us so that we could make things disappear based, for instance, on temperature while we are inside a field of density, something like that, yes. And this is actually demonstrated here on the next slide, if it moves up. So this is actually exactly the same thing, and I can actually manipulate the window, but well, you can see that it is extremely small, but it proves that Mathematica can actually represent this kind of adventure. So I'm going to try to manipulate this window. Yeah, it is. Okay, very difficult, but probably the red dots will change, and they change. So it is actually possible to manipulate the window on a virtual reality environment developed entirely on Mathematica. So this is interesting. Well, now trying to push to our topic that was volumetric information. we can do exactly the same thing. This is also an example from the documentation, and we can also individualize a specific points in space based on their value and based on a dimension reduction. In this case, the dimension reduction is we reduce the 4D information into the Z location, Z coordinate, and the field value. Yes, and so when I reduce in this direction, I'm actually just picking high points on the image in terms of their locations. If I reduce, I'm picking the entire area, and this I'm just picking the bottom information. I can actually add contours, but well, that's the easy part. That's adding 2D information into the 3D world, and it will probably do it, and there it is, yes. And so to finish, well, I hope you have enjoyed. First, it is just to see to what point we could push Mathematica to do this kind of visualization. It could be fun to have these kind of things in the future. Yes, like to have pre-prepared virtual reality environments to explore specific functions, specific fields, things like that. Yeah. So I hope it motivates someone to explore that area. And so, can I use Mathematica as an excuse? For the acquisition of a virtual reality headset. Well, I don't think that we can use it as an excuse for a 500 euros equipment, but probably for the cardboard, yeah, probably it's already enough. Yeah. So, thank you very much.